Welcome back to the deep dive. For you listening at home, you probably know we track a lot of advanced manufacturing, and we are way past the era of just brute force machining.
Oh, absolutely. I mean, it is a completely different world out there now.
Right. And today we've got this really fascinating stack of engineering briefs, and our mission for you today is to basically decode the specialized vocabulary of precision mechanical engineering.
Yeah, specifically looking at, well, these 5 critical concepts that engineers use to manufacture these incredibly delicate parts. Things with just microscopic tolerances.
And doing it without completely destroying them in the process, which seems to be the hard part.
Right, exactly. I mean, the language in these notes, it tells this crazy story about managing extreme physical tension, like take the flex spline component, for example.
Okay, yeah, I saw that in the brief.
Yeah, they repeatedly highlight this challenge of machining what they call a thin-walled section.
Which means exactly what it sounds like.
Yeah. Pretty much. It's a geometry where the wall thickness is just incredibly small compared to the part's overall footprint. So, because there's barely any mass, there's basically zero rigidity.
So it's essentially like trying to carve this highly detailed sculpture out of a hollow eggshell.
Oh, that's a perfect way to put it.
Like one wrong move and the whole thing just collapses.
Exactly. And the immediate physical consequence of putting a high-speed cutting tool against that precarious eggshell is vibration. Severe self-excited vibration.
Wait, like shaking the part to pieces?
Yeah, in the industry they call it chatter.
Chatter. Because the material is what, just too fragile to push back against the blade?
Right, it just bounces. And if left unchecked, chatter leaves these massive gouges all over your surface finish, and it literally shatters your precision tools.
Oh, wow. So how do they fix that?
Well, they have to implement chatter suppression. In this flex spline case, the notes say they used an active damping mandrel inside the part.
Okay, active damping mandrel. How does that actually work in practice?
You can think of it as like an intelligent shock absorber. It sits inside that hollow space and actively applies counterpressure.
Oh, I see.
Yeah, so it absorbs the kinetic energy in real time, which keeps that thin wall rigid against the cutting blade.
Okay, but stepping back for a second, if taking a blade to these sensitive walls causes so much trouble with shatter and everything, why are we even cutting them at all? Like, couldn't we just press or mold the metal into shape?
And that is the exact pivot these engineers make. They use a process called flow forming.
Flow forming. Okay, meaning what?
It's an entirely chipless process, so instead of cutting material away, they use massive rollers to squeeze and, plastically deform the metal into its final shape.
Oh, that is wild. So it's like a potter's wheel, but for high-strength metal alloys.
That is exactly what it's like, and what's really interesting is why they do it. I mean, flow forming doesn't just bypass those cutting vibrations.
Right.
It actually drastically improves the material's structural integrity. Because when you cut metal, you sever its internal grain lines. Oh, sure, you're breaking the structure.
Right. But when you flow form it, you are stretching and aligning those grain lines along the shape of the wall. It creates a vastly superior grain structure.
Wait, hold on though. If you're cold squeezing a metal alloy with enough force to literally rearrange its grain structure, I mean, you're pumping a massive amount of mechanical energy into that part. Doesn't the metal just hold on to that trauma?
Oh, it absolutely does.
Yeah.
Yeah, all that trapped mechanical energy becomes internal stress. Which brings us to their next concept, residual stress management.
Okay, so managing that trapped energy.
Exactly. Because if you don't use targeted thermal treatments to relax it, the second you unclamp that newly formed part from the machine, it geometrically distorts.
Wait, really? It just bends on its own?
Literally warps itself out of tolerance just sitting on a table, all because it's trying to release that pent-up energy. That is insane.
Yeah.
It basically just wants to spring back. But that creates a massive logistical headache, right? If the part is so sensitive that the internal stress of being formed makes it warp, how do you actually hold it to do the final submicron finishing work?
Well, you can't. Not with regular tools.
Because traditional mechanical clamps would just crush it.
Exactly. So you abandon mechanical clamps entirely and you move to vacuum chucking.
Vacuum chucking. Suction, basically.
Right. You place the part on a specialized fixture and pull a vacuum underneath it. That distributes the holding force perfectly uniformly across the whole surface area.
I love that. It's like trying to hold a wet sheet of paper perfectly flat. If you grab it with heavy metal tongs, you crumple the edges instantly.
Yeah.
But if you press it against the glass window and use hundreds of tiny suction cups on the back, it stays completely smooth.
Precisely. There are no localized pressure points to cause deformation. And, the precision is staggering. The briefs mention a diaphragm component where they used vacuum chucking to keep the flatness within 2 microns.
2 microns.
Yeah, you just cannot physically achieve that with gripping jaws.
So looking at this whole chain of events for you listening, you start with the inherent danger of thin-walled sections. You have to invent active damping mandrels just to stop the chatter. Then you pivot to flow forming to align the grain.
Right.
Then you thermally manage the residual stress so it doesn't twist itself into a pretzel. And finally, you gently pin it down with vacuum chucking.
It really is a completely different paradigm of manufacturing. You aren't overpowering the material anymore. You are basically negotiating with it at a microscopic level.
Which leaves you with this to mull over, honestly. If engineers are forced to go to these absolute extremes just to hold these parts without destroying them, what impossibly precise, futuristic technologies are these delicate components ultimately going inside?